Chapter 12 Nuclear Transformations. This is the interior of a tokamak fusion test reactor at the Princeton Plasma Physics Laboratory. In December 1993, this reactor produced 6.2 megawatt of fusion power for 4 seconds from a deuterium-tritium plasma confined by strong magnetic fields. Despite the strength of the forces that hold nucleons together to form an atomic nucleus, many nuclides are unstable and spontaneously change into other nuclides by radioactive decay, and all nuclides can be transformed by reactions with nucleons or other nuclei that collide with them. In fact, all complex nuclei came into being in the first place through successive nuclear reactions, some in the first few minutes after the Big Bang and the rest in the stellar interiors. The principal aspects of radioactivity and nuclear reactions are considered in this chapter. Radioactive decay are of five kinds. No single phenomena has played so significant role in the development of nuclear physics as radioactivity, which was discovered in 1896 by Antony Becquerel. The three features of radioactivity are extraordinary from the perspective of classical physics. When a nucleus goes alpha or beta decay, its atomic number changes and it becomes nucleus of a different element. Thus, the elements are not immutable, although the mechanism of their transformation would hardly be recognized by an alchemist. Thus, the elements are not immutable, although the mechanism of their transformation would hardly be recognized by an alchemist. The energy liberated during radioactive decay comes from within individual nuclei without external excitation, unlike the case of atomic radiation. How can this happen? Not until Einstein proposed the equivalence of mass and energy could this puzzle be understood. The energy liberated during radioactive decay comes from within individual nuclei without external excitation. Radioactive decay is a statistical process that obeys the laws of chance. No cause-effect relationship is involved in the decay of a particular nucleus, only a certain probability per unit time. Classical physics cannot account for such behavior, although it fits naturally into the framework of quantum physics. The radioactivity of an element arises from a radioactivity of one or more of its isotopes. Most elements in nature have radioactive sorry no radioactive isotopes, although such isotopes can be prepared artificially and are useful in biological and medical research, such as tracers. The radioactivity of an element arises from radioactivity of one or more isotopes. Although most elements have no radioactive isotopes, although such isotopes can be prepared artificially and used in biological or medical research as tracers. The procedure is to incorporate a radionuclide in a chemical compound and follow what happens to the compound in a living organism by monitoring the radiation from the nuclide. Other elements such as potassium have stable isotopes and some radioactive ones. A few such as uranium have only radioactive isotopes. The early experimenters among Rutherford and his co-workers distinguished three components in the radiation from radionuclides. These components were alpha, beta, and gamma, which were identified as helium nuclei, electrons, and high-energy photons respectively. Later, positron emission and electron capture were added to the list of decay modes. Further, alpha particle path, gamma path, magnetic field directed into paper, beta particle path, radium sample, and lead box. The radiations from the radium sample may be analyzed with the help of magnetic field. Alpha particles deflected to the left and hence they are positively charged. Beta particles are deflected to the right, hence they are negatively charged. Gamma particles are not affected and hence they are unchanged. Figure 12.3 shows five ways in which an unstable nucleus can decay together with the reason for the instability. The neutrinos given off when the nuclei emits or absorbs electrons are discussed in section 12.5. Examples of nuclear transformations that accompany the various decays are given in 12.1. So for example, alpha decay, 238 uranium decays by alpha, it gives thorium and helium atom. Beta decay, if carbon 14 decays by it gives nitrogen and an electron. If positron emission, copper becomes nickel and positron. Electron capture, copper takes an electron and becomes nickel, and gamma decay, strontium decays into strontium plus gamma decay. The star denotes the excited state of strontium. The star denotes an excited nuclear state, and gamma denotes gamma ray photon. So alpha particles from radioactive materials are stopped by a piece of cardboard. Beta particles penetrate the cardboard but are stopped by a sheet of aluminium. Even a thick slab of lead cannot be stopped, may not stop the gamma rays. So gamma rays, gamma decay. So original nucleus decay event, emission of gamma ray reduces energy of nucleus. Final, this is the final nucleus. Nucleus has excess energy. Reason for the instability is that nucleus has excess energy. Alpha decay, emission of alpha particle reduces the size of nucleus. So emission of gamma ray reduces energy of nucleus. Emission of alpha particle reduces the size. Emission of electron by neutron in a nucleus changes the neutron to a proton. Beta decay, emission of electron by neutron in nucleus changes the neutron to a proton. Nucleus has too many neutrons relative to a number of protons. Capture of electron by proton in nucleus changes the proton to a neutron. Nucleus has too many protons relative to the number of neutrons. Positron emission. Emission of positron by proton in nucleus changes the proton to a neutron. Nucleus has too many protons relative to the number of neutrons. Emission of positron by proton in a nucleus changes the proton to a neutron. Electron capture में emission capture of electron by proton in a nucleus changes proton into a neutron. Emission of electron by neutron changes neutron to a proton. तो ऐसा क्यों होता है? न्यूक्लियस हैज टू मेनी न्यूट्रॉन्स तो फिर बीटा डिके होता है. अगर न्यूक्लियस में टू मेनी प्रोटॉन्स तो इलेक्ट्रॉन कैप्चर हो जाएगा. And if nucleus has too many protons relative to the number of neutrons तो पॉजिट्रॉन emission हो जाएगा, पॉजिट्रॉन emission हो जाएगा. About Becquerel. Anthony Henry Becquerel was born and educated in Paris. His grandfather, father, and son were also physicists, all of them in turn professors at the Paris Museum of Natural History. Like his grandfather and father, Becquerel specialized in fluorescence and phosphorescence, phenomena in which a substance absorbs light at one frequency and, and remits at another frequency. In 1895, Roentgen has detected X-rays by the fluorescence they cause in an appropriate material. When he learned of this early in 1896, Becquerel wondered whether the reverse process might not occur with intense light stimulating fluorescent material to give off X-rays. He placed a fluorescent uranium salt on a photographic plate covered with a black paper, exposed the arrangement to the sun, and indeed found the plate fogged when he had developed it. Becquerel then tried to repeat the experiment, but clouds obscured the sun for several days. He developed the plates anyway, expecting them to be clear, but to his surprise they were just as fogged as before. In short time he had identified the source of penetrating radiation as uranium in the fluorescent salt. He was also able to show that radiation ionized gases and that part of consisted fast charged particles. Although Becquerel's discovery was accidental, he realized its importance at once and exposed various aspects of radioactivity of uranium for the rest of his life. He received Nobel Prize in 1903. In 1895, Roentgen has detected X-rays by the fluorescence they cause in an appropriate material. When he learned of this early in 1896, Becquerel wondered whether the reverse process might occur, with intense light simulating a fluorescent material to give off X-rays. He placed fluorescent uranium salt on a photographic plate exposed to the arrangement of the sun and indeed found the plate fogged when he had developed it. Becquerel then tried to repeat the experiment, but clouds obscured the sun for several days. He developed the plates anyway, expecting them to be clear, but to his surprise, they were just as fogged as before. In the short time, he has identified that the source of penetrating radiation as the uranium in fluorescent salt. Radioactivity and the Earth. The helium 6 helium is unstable. What kind of decay would you expect? So this has extra neutrons. So whatever has neutrons, it will go beta decay. All of whose neutrons and protons are in lowest possible has 4 neutrons, where helium 2 has only 2, is due to excess neutrons. So this suggests helium undergoes negative beta decay to become lithium isotope whose neutron proton ratio is more consistent with its stability. Radioactivity and Earth. Most of the energy responsible for the geological history of the Earth can be traced to the decay of the radioactive uranium, thorium, and potassium isotopes it contains. The Earth is believed to have come into being perhaps 4.5 billion years ago as a cold aggregate of smaller bodies that consisted largely of metallic iron and silicate materials that had been circling the sun. Heat of radioactive origin accumulated in the interior of the infant Earth and in time led to partial melting. The influence of gravity then caused the iron to migrate inward to form the molten core of today's planet. The geomagnetic field comes from the electric currents in this core. The lighter silicate rose to form the rocky mantle around the core that makes up about 80% of the Earth's volume. Most of the Earth's radioactivity is now concentrated in the upper mantle and the crust relative thin outer shell where the heat it produces escapes and cannot collect to remelt the earth. The steady stream of heat is more than enough to power the motions of the giant plates into which the earth's surface is divided and mountain building earthquakes and volcanoes associated with these motions. The activity of a sample of any radioactive nuclide is rare, at which nuclei of its certain constituent atoms decay. If n is the number of nuclei present, the radioactivity is given by dn by dt. The minus sign indicates to make r as a positive quantity since dn by dt is of course intrinsically negative. 1 becquerel is equal to 1 decay per second. The activity encountered in practice are usually so high that the megabecquerel 10 to the power 6 and gigabecquerel are often more appropriate. The traditional unit of activity is curie, which is often originally defined as the 1 gram of radium, which is defined as the activity of 1 gram of radium. Because the precise value of curie changed as methods of measurement improved, it is now arbitrarily defined as 3.7 into 10 to the power 10 decays per second, or 37 gigabecquerel. The activity of 1 gram of radio is few percent smaller. Ordinary potassium has an activity of 0.7 microcurie per kilogram because it contains small proportion of radioisotope potassium. Radiation hazards. The various radiations from radionuclide ionized matter through which they pass, X-ray ionized matter too. All ionizing radiation is harmful to the living tissue, although if the damage is slight, the tissue can often repair itself with no permanent effect. Radiation hazards are easy to underestimate because there is usually a delay, sometimes of many years, because an exposure and some of its possible consequences. These consequences include cancer, leukemia, and changes in DNA of reproductive cells that lead to children with physical deformities and mental handicaps. Radiation dosage is measured in sieverts. Radiation dosage is measured in sieverts, where 1 SV is the amount of any radiation that has some biological effect that produces when 1 kg of body tissue absorbs 1 joule of X-rays or gamma rays. Although radiobiologists disagree that the exact relationship between radiation exposure and likelihood of developing cancer, there is no question that such a link exists. The International Commission on Radiation Protection estimates an average risk factor of 0.05 sieverts per sieverts. This means that chances of dying from cancer as a radiation are 1 to 20 for a dose of 1 sievert, 1 in 20,000 for a dose of millisieverts. Figure 12.4 shows the chief sources of radiation dosage on a worldwide basis. The most important single source is the radioactive gas radon, a decay product of radium whose origin traces back to the decay of uranium. Uranium is found in many common rocks, notably granite. Hence, radon, colorless, odorless, is present nearly everywhere, though usually in amounts too small to endanger health. Problems arise when houses are built in uranium-rich regions, since it is possible to prevent radon from entering such houses from ground under them. Surveys show that millions of American homes have radon concentrations high enough to pose a non-negotiable cancer risk. As a cause of lung cancer, radon is second only to cigarette smoking. The most effective method of reducing radon levels is an existing house in the hazardous region seems to be an exact air with fans from underneath the ground floor and disperse it into atmosphere before it can enter extract air with fans from underneath and the ground floor and disperse it into atmosphere before it can enter the house. Other natural sources of radiation dosage include cosmic rays from space and radionuclides present in rock, soil, and building materials. Food, water, and human body itself contains small amounts of radionuclides of such elements such as potassium and carbon. When useful processes involve ionizing radiation, some employ such radiation directly as in X-rays and gamma rays used in medicine and industry. In other cases, radiation is an unwanted but an inescapable byproduct, notably in the operation of nuclear reactors and in the disposal of their waste. In many countries, the dosage limit for workers, about 9 million worldwide, whose jobs involve ionizing radiation, is 20 millisieverts per year. For a general public which has no choice in the matter, the dose limit for non-background radiation is 1 million sievert per year. An appropriate balance between risk and benefit is not always easy to find where radiation is concerned. This seems particularly true for medical exposures, many of which are made for no reason and do more harm than good. The once routine X-raying of a symptomless young woman to search for breast cancer is now generally believed to have increased, not decreased, the overall death rate due to cancer. Partially dangerous is the X-raying of pregnant women. Until not long time ago, the routine procedure which dramatically increases the chances of cancer in their children. Of course, X-rays have many valuable applications in medicine. The point is that every exposure should have a definite justification that outweighs the risk involved. An ordinary chest X-ray using modern equipment involves radiation dose of about 0.017 millisievert, much less than in the past. However, CT chest scan involves the considerable dosage of 8 millisievert. CT scans of children pose serious, especially serious risk and need equally serious justification. Radionuclides in rock soil buildings, medical X-rays and nuclear medicines, diet, cosmic rays and radon. The activity of radionuclide decreases exponentially with time. The half-life is the time needed for an annual activity to drop by half. The mean life for radionuclide is 1.44 times its half-life. So that's all in this one. See you in the next.